All right, welcome everybody. In this video, we are going to look at an example that's going to illustrate the concepts behind what are called eigenvectors and eigenvalues of a matrix. And so these are going to be really helpful information to know about a matrix. In particular, eigenvalues for anyone that has taken a differential equations class and studied systems of differential equations. Eigenvalues are really critical in understanding the long-term behavior of certain solutions of those equations. They also provide really critical information in engineering and physics and chemistry. So for anybody that's working in STEM fields, this may be one of the most important applications from linear algebra, which is analyzing the eigenvectors and eigenvalues of a matrix. So let's begin with an example. So let's consider the 2 by 2 matrix A, whose first column is 0, -4, and the second column is -2, 2. And let's consider two vectors. U is the vector 1, 1, and V is the vector -1, 1. And let's see what happens when we multiply vector U by matrix A, and what happens when we multiply vector V by matrix A. And for A times U, what we get is a vector -2, -2. And notice that this is a scalar multiple of the vector that we started with. So this is equal to -2 times the vector U that we started with. So what I can see in this relation is that multiplying the vector 1, 1 by this matrix A is equivalent to just multiplying this vector 1, 1 by the scalar -2. So this is a really special relationship that multiplying matrix A by this matrix 1, 1 is equivalent to multiplying that vector just by a scalar, in this case by the scalar -2. So let's see what happens when we take the product of matrix A times vector V, which now is -1, 1. And so calculating this product, we get -2, 6. And notice this is not a scalar multiple of the vector that we started with. So we don't have this special relation that multiplying vector V by matrix A is equivalent to just multiplying vector V by some scalar. So this had a really nice special property when we multiplied the vector 1, 1 by matrix A. We did not observe this special property when we multiplied the vector V by matrix A. So now we're ready to define these terms, eigenvalues and eigenvectors, in light of this example. So an eigenvector of an n by n matrix, and it's really important to point out here that we can only discuss eigenvalues and eigenvectors for square matrices where the number of rows and the number of columns are the same. So an eigenvector for a square n by n matrix A is a non-zero vector x such that multiplication by the matrix A is equivalent to scalar multiplication by some scalar lambda. So in this case, we would say the vector 1, 1 was an eigenvector of this matrix. The vector -1, 1 is not an eigenvector of matrix A because we don't have this behavior that A is acting on this vector by multiplication by a scalar. The scalar lambda is called an eigenvalue if there is a non-trivial solution x to the equation ax is equal to lambda x. So in this case, we would say that -2 is an eigenvalue because this equation a times x equals -2 times x has a non-trivial solution, namely the vector u, 1, 1. So we would say that -2 is an eigenvalue of this matrix A, and this vector, in this case 1, 1, we would say is an eigenvector corresponding to the eigenvalue -2. So just to get all of these terms straight, we would say -2 is an eigenvalue with corresponding eigenvector 1, 1.